Just give me a minute. Set this up. Okay, so now let's go to the analysis part of it. What are we going to analyze? We're going to analyze the side channel traces to recover the key. And the side channel trace is actually present in your lab 4 folder, lab 3 folder. Though we have learned how to capture traces, we're not going to work with exactly those traces. There are some traces that are pre-captured for you in the lab 3 folder, and you can see it in the file is called waveform. You just download that CSV file. Just download the CSV file so let me explain how to interpret the CSV file. So the first 2 columns are important. So the first column is nothing but the plain text. So these are the plain text that you have used to encrypt. The plain text that you have encrypted is the first column. So this is plain text 1, plain text 2, plain text 3, plain text 4. And this is the corresponding ciphertext 1, ciphertext 2, ciphertext 3, ciphertext 4. And if you look at the other columns here, so starting from the third column, this is basically the side channel trace. So you see the LO waveform, right? So the LO waveform is basically interpreted like this. So if this is your LO waveform, then all the points are basically interpreted between 0 and 1. So every point is basically having a value between 0 and 1. So that's why you see values like 0.406, 0.442, 0.39, 0.362, 0.414 and so on. Okay? And in the waveform that you have actually captured, in the waveform file that we have given to you, there are actually 2500 points for each waveform. So each waveform basically contains 2500 points. So you can basically just count the number of points, and in the waveform file that we have given to you, there are 2500 points. Is this clear? So essentially what you have in the waveform file is the plain text, the ciphertext, and the corresponding power waveform. So this additional power waveform is the side channel information that you have. So if I go back to the previous discussion, if I just give you the plain text and the ciphertext pairs, there is no known algorithm that you can use to recover the secret key. It's computationally infeasible, but the game suddenly changes if I give you access to this additional information, power side channel information, and then suddenly you can do a very simple analysis to actually recover the secret key. That's what we're going to learn in this lab session. So in a way, if you think about it, I'm giving you the plain text, the ciphertext, and the corresponding side channel trace. So you can consider the side channel trace to be a vector or a trace. And then I'm giving you the second plain text, the second ciphertext, and the corresponding side channel trace. And then a third one, and the fourth one, and so on. And can you tell me how many such plain text ciphertext pairs have I given you in the waveform file? How many such pairs do you have? Yeah. So there are about 110 plain text ciphertext pairs along with their corresponding side channel information that you have. And in order to recover the secret key, all you need is just this. You just need this information to recover the secret key. Now you see how the game changes, right? So if I don't give you this additional side channel information, then even if I give you 1,000,000 pairs or 1,000,000,000 pairs, you'll not be able to recover it. But with access to side channel information, the amount of effort required comes from 1,000,000 or 1,000,000,000 or even higher to just a few hundred or just 100 traces. And this is all you need to actually recover the entire secret key. So in order to understand the attack, we need to know what is happening within the AES encryption algorithm. So let's try to understand that a bit. This is the internal of the AES encryption algorithm. For the attack, you don't have to understand everything. You only have to understand what happens in step 1 and step 2. So let's try to understand what step 1 and step 2. It's actually quite simple. So you start with the plain text, and the first operation after the plain text, the first operation on top of the plain text is something called add round key. So what you do with add round key is you have 16 bytes of the plain text. Why 16 bytes? You remember the plain text is 128 bits, so 128 bits is 16 bytes. So you have 16 bytes of the plain text, and you have 16 bytes of the key, and you're just going to XOR every byte of the plain text with every byte of the key, and you're going to get the corresponding output. Is this clear? It's just a very simple XOR operation. So you're XORing the plain text with the key, and you're getting the corresponding intermediate state. Is this clear? Yeah? So this is the first operation, which is add round key. So you're basically mixing the plain text and the key together using the XOR operation. The second operation is called sub bytes, substitution of bytes. What you do is, on top of the output of the add round key, you will perform a sub bytes operation. So what is a sub bytes operation? So you take one byte and you substitute that byte with another byte. So if it's 0, 0, you substitute 0, 0 with something else. If it's 1, 2, you substitute 1, 2 with something else. So you substitute a byte with another byte. So let's see how to do that. So how do you do this substitution bytes operation is using a lookup table. So use the lookup table to replace one byte with another byte, and this is how it's done. 1 minute. Yeah. So this is how we actually do the substitution bytes operation, right? So let me explain this a bit. Oh my God. So let's say you have a byte which is 0x45. So let's say you have 0 byte 0x45, and you are supposed to do the sub bytes operation on 0x45. So what you do is you split the byte into the first 4 bits and the second 4 bits. The first 4 bits is 4, the second 4 bits is 5, and then you simply use this lookup table. So this is your first 4 bits and this is the second 4 bits. So can you tell me what is this? What is the output of subbytes of 45? So subbytes of 45 would be 4 and 5. That will be 6e. And similarly, if you want to do subbytes of 35, that would be 96. So it's a very simple lookup table operation where you replace one byte with another byte. Is this okay? So now going back to the AES operation. So you start with the add-on key where you mix the plain text with the key using the XOR operation, and after that you perform the subbytes operation where you take a byte and you replace it with another byte. Cool? So let's try to understand this a bit more. So if we consider the plain text to be let's consider the plain text to be x0, x1, x2, x3 until x50, and the key, how many bytes are there in the key? 16 bytes, right? So k0, k1, k2, k3, k15. So what happens, now let's try to see what happens in step 1 and step 2. So in step 1 what happens? Can anyone tell me? Add-on key where you XOR the first byte of the plain text with the first byte of the key. Am I correct? So you XOR it and you get the output, and on top of the XOR what do? You do the subbytes operation, right? And then you get, let's consider this to be y0. Y0. And then what happens? What's the next step? You simply repeat this operation again on the second byte. So you take the second byte of the plain text, second byte of the key, and then you get y1. And you do this operation for the third byte, y2, y3, y4. Is this clear? So essentially, this is step 1, and after step 1 you do step 2. And you see these steps are all happening byte-wise. So you're taking every byte and you're operating on every byte individually. So now, in order to do the side channel attack, what we're essentially doing, what we're going to do is, we are trying to recover information about this intermediate value, y0, y1, y2, y3, y4, all the way until y15. And if we manage to gather some information about the intermediate values, then we manage to recover the key. And what we're going to do is we're going to try to recover information about these intermediate values through the traces that you captured in the lab, or rather the waveform file that I gave you. So this is what we're going to try to do. Is it okay? So we will attempt to recover information about this intermediate state through the power side channel traces, and with that we'll be able to recover the key. Are you with me until this point? Cool. So now let's one more point that I wanted to highlight is the way you're going to recover the key. So can you tell me how many bytes are there in the key? There are 16 bytes, right? So the way the attack works is you try to recover the entire key one byte at a time. So you first do an attack to recover byte k0, then you recover k1, k2, k3 and so on. You do it in a sequential manner. You cannot recover the entire key in one shot. You will do an attack to target the first key byte, then you will do an attack to target the second key byte, third key byte and so on. Okay. One more thing is, actually there is a recording of this lecture, or rather this lab session, so later you can actually review it at your convenience. Cool. So now what we're going to do is we are going to try to recover this intermediate state. And for that, let's do some exercises, right? Cool. Or let me give you a small exercise right now. So can you try to tell me the relation between y0 in terms of x0 and k0? Can you write an equation that represents y0 in terms of x0 and k0? How will you do that? So what's the relation between y0, x0 and k0? How will you represent this? So let's just take this example. So what happens to x0? x0 is first XORed with k0, and on this byte you are basically performing the subbytes operation. Am I correct? Is this clear? So now you can also generalize this. So what's actually happening is this not only happens for the first byte, it happens for all the 16 bytes. So essentially the general relation is yi is subbytes of xi XOR ki. Am I correct? So the value of yi depends on ki. Right? So if you are able to recover yi, you will be able to recover ki, and I basically goes from 0 until 15. So that's like all 16 bytes. And now, in order to understand the attack, what we're going to do is we are going to focus only on recovering the first key byte. So if you learn how to recover the first key byte, then you can repeat the attack to recover all the key bytes. So we are only going to focus on how to recover the first key byte, which is y0 or rather k0. So we are only going to focus on recovering k0. So in order to recover k0, what are you supposed to learn about? You're supposed to learn about y0, right? Only then you can recover k0. But the question is, y0 is basically data. So y0 is data that you're trying to learn, and what you have is basically just the side channel traces. So side channel traces is nothing but power. So now you're supposed to relate the data and the power, and the question is, how do you actually make the relation between the data and the power? So how do you actually construct a relation between the data and the power? So we do not know how to relate the data into the power, and that's the reason why we need a concept called a model. So let's try to look at that. So in order to understand the relation between the data and the power, we'll have to understand how does the device leaks information through side channels. So for example, you all know inside a chip there is memory, there are registers that store data, right? Now let's take the example of a simple 8-bit register. So let's say you have an 8-bit register here which has a value of 0111, 0101, and your switching or the device during the computation switches the value from this to this. Okay? And now can you think about what would the power actually depend on? So I've given you that the initial data is this, the final data is this, And can you tell me what would the power basically depend on, or how would you go about computing the power from this data? I'm not asking you the exact power, but I'm just asking you the relation. So if I were to ask you what would the power depend on, can you think about what would the power depend on? Sorry? Yeah, exactly. It basically depends on how many bits basically switched from here to here. So the more the number of bits that switch, more power. The lesser number of switches that switch, you have lesser power. Do you agree with me? For example, if this register always had the value of never switched, if the register never switched and always just had this value, then the device does not need to do any extra effort, or does not need to put any extra effort. It just has to maintain the same value. But when the device has to switch, it has to consume some power, and the amount of power that it needs depends on how many bits it's trying to switch. So in order to compute what's the power, you would simply need to calculate how many bits actually changed from this point to this point. Can you count how many bits changed? You will see that 6 bits have actually changed from the first value to the second value. So this is basically nothing but the power consumption of this operation. Is this clear? So if I am just going back a bit, we are basically trying to understand how to relate the data to the power. And in order to build this relation, I'm giving you this example. So for any operation, whenever there is a data change, there is power consumption, and the difference in the number of bits of the data basically determines the power consumption. So going back to the AES operation, you do agree with me that during the AES operation, you are actually computing y0, y1, y2, y3, y4, right? So you're computing all these intermediate states, and if you sort of superimpose this on the power side channel trace, you will actually see that at certain points would correspond to y0, y1, y2, y3, y4, y5, and so on, right? Until y16. Do you agree with me? The power waveform, the reason it's changing is because the data changes, and if you zoom into the power waveform, you should be able to see the manipulation of y0, y1, y2, y3 across time. Do you agree with me? Right? So now the question is, how do I, from this value of the power, how do I find a relation to the data? So this is how we do that. Let me just so the way the chip works is the register would always have an initial value of all ones, and then it would switch to, let's say this is your y0, okay, and for y1 the register would again, and so what is the power consumption for y0 then? Can you tell me what would be the power consumption for y0? This would be 4, exactly. Why? Because in order to store y0, the device had to switch 4 bits. So the power consumption is basically 4. Similarly, if the device has to switch to y1, it will always have a default state and then it will switch to the actual value. So if this is y1, then what's the power consumption of y1? That would be 2, right? So essentially, you can sort of encapsulate all of this into one term, which is called Hamming weight. So in the Hamming weight model, you're basically building a relation between the data and the power. And how do you go about computing the Hamming weight of data? you simply compute the number of ones in the data. So how many ever number of ones are there in the data? So you take the data, you convert it into binary, and in the binary representation, how many ever number of ones are there in the data? That's nothing but the power of the data. So if I give you data, you should be able to compute the power using the Hamming weight relation. So now I can just do a simple manual exercise to calculate the Hamming weight of 50 in decimal, 99 in hexadecimal, and so on. I'll just give you a couple of minutes. So let's try to understand how to compute the power. So let's say your data is 50 in decimal. 50 in decimal would be 110010. So the Hamming weight of this would be 3. And 99 in hexadecimal would be 1001, and that would be 4, and so on. So you can do this computation, right? So now let's try to also code it, program it. So if you go to NTU Learn, you'll also see this program called just a moment. Yeah, there's something called CPA incomplete. So can you see this one, CPA incomplete.py? So just download that and again open it in PyCharm. Let's try to do that. Okay. So what I want you to do is, so there is actually a definition, so there's a function called Hamming weight. So can you write code to calculate the number of ones in a byte? So just write a function to compute the Hamming weight of any data that you give to it. You can use ChatGPT or any AI or Claude or whatever. So just write a function to compute the Hamming weight of the data. Like there are some Python packages that you can use like bin count and stuff like that. So you can implement in several number of ways. I'm not going to explain how it's done. Can be studied later. But just to verify this, you can just say a equal to maybe 32, and then you can just compute Hamming weight of 32 or Hamming weight of 8, and you can just this program, okay, there's another, just you can just delete this part. It just gives you some errors. You just run this and you should be able, I mean obviously it will return you some errors because the program has multiple tasks and you're supposed to complete everything, but because the tasks are not done yet, you will see some errors, but nevertheless you should see the output of 1. So 1 basically indicates that so you see Hamming weight of 32 is 1 because 32 is basically 1 followed by 4 zeros. So my Hamming weight function works correctly. Cool. So now, we now know how to compute Hamming weight. Great. So let's move to the attack analysis. Right. So in this Python program, what we're going to do is we're going to understand how to implement the attack on some simulated traces. So we'll go through the attack step by step. So again, going back to this picture. So we are going to solely focus on Y0. Y0 is what we try to recover, and if we recover information about Y0, then we recover K0, and here we were able to basically identify the relation between the data Y0 and power Y0. How do you do that? Is you simply compute the Hamming weight of Y0. Is this okay? So if you want to compute how Y0 would look like in the power trace, you simply can compute the Hamming weight of Y0, and this will give you the power of Y0. Okay, and now let's try to see how the attack basically works. So what we have done is, so for plain text 0, plain text 1, plain text 2, how many plain text do we have? We have plain text 110, but just to simplify it, let's just consider we have 100 plain texts. For each of the 100 plain texts, we have the corresponding SBox output. Am I correct? For each of the 100 plain texts, we can compute the SBox output if we know the key. Am I correct? So we're going to try, and for the SBox output, we can also compute the power of the SBox output, right? How do you compute the power? You simply compute the Hamming weight of the data. Am I correct? So let's try, probably it's not very clear now, but let's just try to do some experiments in the Python program. So let's go back to the Python program. And here what we have done is I've just generated a random set of plain text bytes. So what I'm doing is I'm just generating 100 random plain text bytes, and these bytes are something similar to the first bytes of the plain text. Because we are attacking the first key byte, we will only focus on the first plain text bytes. So I'm just trying to generate the first plain text byte of every plain text. So I'm just generating random values in the Python program. So here I'm just generating random values in this list. I'm generating a random value between 0 and 255, and I'm just printing it here. Cool. So now if you just execute this Python program, you will be able to see something like this. Do you see this? So this is basically the first byte of all the plain texts. So this is the first byte of the first plain text, first byte of the second plain text, first byte of the third plain text, and so on. Because in order to do the attack, we need to sort of recover the first byte of the plain text. Instead of extracting it from the Excel sheet, I'm just generating a random set of plain text bytes. Is that clear? So I'm just generating the first set of plain text bytes, and I'm generating 100 of them. Why 100? So here I'm just iterating for these many number of times, and this is actually chosen as 100. Cool. So I'm just generating 100 plain text bytes, and now what I'm going to do is I'm going to build the SBox output for all these plain text bytes, assuming that my key value is 0x20. So I'm going to assume that my key byte value is 0x20, and now I'm going to construct the SBox output for all these plain text bytes. And I want you to actually store it in this particular array. Can you do that? So what I'm telling you is you have the first bytes of all the plain texts, and I want you to compute the SBox output assuming that the key value is 0x20. You don't know the key value obviously, but just to make the attack, make you understand the attack, I'm just assuming that the key value is 0x20. Let's first try to compute the SBOX output for all of these plain text bytes. And you're supposed to store the output in this leaky SBOX output value array. Can you do that? Yeah. So this is how the code would look like for computing the SBox output. So what you do is you simply take every byte or every element of this particular list, you XOR it with the key 0x20, and then you simply compute the SBox on top of that. So the SBox is also given here for you. You see, this is the SBox. So how do you compute the SBox of a value? You simply find, if you want to find SBox of the nth value, you simply find the nth element in this list. That's the SBox output. Right? Do you get that? So if you want to find SBox of 0, 0, that's nothing but the first element. You simply index the first element of the array. SBox of 0, 1 is 7C, SBox of 0, 2 is 7, 7, 0, 3, and so on. So that's the reason why here we have simply, so once you have the output of the add-on key, we have simply computed the SBox on top of it by indexing the corresponding element in the SBox array. Is this clear? If I go back to the slides, the SBox output is, so the SBox is simply a lookup table, right? So here it's shown as a 2D array, but in essence you can also implement it as a 1D list as well, a single dimensional list, right? So you just arrange the elements from 6 to 3, 7C, 7, 7. So you just arrange all the elements in one list that has 256 elements. And in order to find the SBox of a value, you simply find what value is present in that particular index, and that gives you the output of the SBox. And this is the so this is the logic to basically compute the SBox output for all the plaintext bytes. I just have it here for a minute, then we move on to the next step. Okay, let's backtrack a bit again, just to keep you in, like, give you the context of where we are, right? So what we're essentially doing is we have the plain texts that we encrypt, and we are simply extracting the first byte of the plain text. And on top of the first byte of the plain text, I'm just computing the SBox output. I'm assuming that the key value is 0x20, but the key value could be anything. But just to get you in the groove, we're just doing some exercises. And here we're just assuming that the key byte value is 0x20. And once you have the SBox output, you want to convert that to power, right? Because at the end of the day, you want to relate the data to the power. So we're going to convert the SBox outputs into power, for which we have to compute the Hamming weight, right? Because Hamming weight is the one that relates the data to the power. So now, as part of the next task, if we go back to the program, you have the SBox outputs in the leaky SBox output value array, right? So we can sort of execute this. And so this is your first bytes of the plain text. This is the corresponding SBox outputs. And now what we want to do is we want to compute the power of the SBox output. And for that we simply compute the Hamming weight of these leaky values. So can you compute the Hamming weight of these values and store them in this list? Can you do that? So we are now doing the third step, which is we are going from here to here. So we are actually computing the power of the SBox outputs. And how do we do that? Is we use the Hamming weight function. So I think we have implemented the Hamming weight function earlier, right? So can you just apply the Hamming weight function on every element of this particular list? Oh, sorry. We have to apply the Hamming weight function on every element of this particular list and then store it in this particular list. Store it in this list. Okay, so how do you, so let's see how to do that. Just give me. I think that code is already there here. So yeah, so here I think we're already just simply computing the Hamming weight on top of all the elements here, and we have stored this in this particular list. So you can just print it out, and I think you'll be able to see. Yeah, this one. See. So you should see something like this. So this is the Hamming weight of the SBox output for the first byte, for the first input, for the second input, third input, and so on. Is this clear? Okay. So now let's go back to this one and see where we are. So right now we are at this step, right? So what we are essentially doing here is we are assuming that the key byte value is 0x20, and we are actually building a model. We are building what's called as a power model for 0x20. So why do I call it the power model? Is because I'm assuming that my key byte is having a certain value, and I am computing what the corresponding SBox output would be, and I'm computing how that corresponding power would look like. So that's why I call this the power model, but this is the power model only for a specific key byte value. The specific key byte value is 0x20. So does that mean that can you compute the power model for all possible values of the key byte? So how many possible values of the key byte are there? So how many possible values can a key byte take? Any guesses? A particular key byte can take how many possible values? 256, right? A key byte can take anywhere between 00, 01, 02 all the way until FF. So the key byte can basically take 256 possible values. So what this means is I can build a power model for all possible values of the key byte. Am I correct? So that will be the next step of the attack. So the next step of the attack would be I would try to build a power model for all possible values of the key byte. So what we have done right now is we have built a power model for 0x20. I mean, this value could have been anything, but I just assumed a value of 0x20 here. And I have built a power model and stored it in this particular list. So now, as the next step, can you build a power model for all possible values of the key byte, and can you store it in power model matrix? So now you need to write code to implement the power model matrix. So why do I call it the power model matrix? Because I am now not only going to compute model for one value of the key byte, I'm going to compute 256 models. So this is one power model. So let's call it M0x20. So what I want you to do is So what I want you to do is I want you to compute M0x00, M0x01, M0x02 and so on until M0xFF. And the reason why I call it the power model matrix is because if you arrange this, it will look like a matrix. For example, your first column could be M0x00. Can you tell me how many elements would there be in a model? How many elements would be there in a model? So if I go back to the previous one, there would be 100 elements, right? Because there are 100 plain text bytes, so I have 100 elements. So the first model would have 100 elements. There will be 100 elements here. The second model would have 100 elements again, and I have the third model, and so on until 0xFF. So I would have 256 models, and each model would have 100 elements. So the size of the matrix would be 256 cross 100. So now I want you to try to write a code that implements the power model matrix. So you know how to compute the model for one possible value of the key byte. I simply want you to replicate it for all possible values of the key byte, starting from 00 until FF. This takes some time to sort of understand this. Give you maybe 5 minutes on this. Don't worry, the solutions for this will be shared with you, so not have to worry about it. But you can try your hands on implementing it. Yeah. Any questions? Please do let me know. Yeah. Yeah, exactly. Exactly. Yeah. So what in the program, what I've actually given you is only one column. So I've only given you one one column that corresponds to SBox operation. But in the actual power trace, you would have like 2500 columns, right? So what you do is simply repeat the operation for all the 2500 columns. And you would ultimately find out the correct column that matches the best. Yeah, exactly. Yeah. The highest correlation will correspond to the correct column that corresponds to SBox operation.
So that's what the sliding diagram bulletin was.
Yeah, exactly.
So you find that SBox
Exactly. No, this is to actually print out all possible Hamming weight functions. So until now what we have done is only compute one model. This is the model corresponding to this value. But I want you to actually compute the model for all possible values. Yeah, these are all possible values.
Yeah.
Yeah. It's only
There's no one out for
access. Yeah, there.
I thought you got somewhere. I think you got somewhere.
Yeah, I'll send it to you. Playing games. Playing games.
okay, what is
No, it's exactly.
okay, this is correct.
This is then the software skill.
That's it. Oh,
No, actually, this operation.
You?
What is
is it like that?
Oh, so now you today already. Surface freeze. Zero four, I think the professors here sort of queuing up.
Oh, sorry? Yeah. Yes.
Yeah, true. Don't mind, we are gonna decorate soon, so might as well take it easy.
Maybe at the level where you can even care about grades and all. Let's say you have a step into the
Yes, I'm kind of there, but it's like it's more like I'm just tired. Like when you think about I mean not really lazy, but this is like rush and last break.
Okay, so
I mean you push yourself and then start push yourself. What's the point? I've been like running for like what, 2 years, 2.5 years.
so there is a secret that I've been hiding from you for a while now. So essentially there is this file called cpa implementation.py in lab 4. This basically just a moment. So in lab 4, you'll be able to see this CPA implementation.py. This basically contains the solution to all the tasks that we did right now. And some of you figured it out before, but so you can just open that Python script and you can see the code for the power model matrix. So you can just, this is the code for the power model matrix. I can just copy it from here and paste it here, and then if you execute this, then I think you should be able to, yeah. So I'm just printing the power model matrix, and as you can see, it's a lot of data, but doesn't matter. So I think I'm able to print the power model matrix. Okay. So now let's get back to the attack. So there's one final step that's missing. We'll be done with this in 10 minutes. Almost done. So just bear with me. So what have we done until now? So until now, what we have done is we have tried to model. We have tried to model something. What have we tried to model? We have tried to model the SBox output for the first byte. Right? So, and how many models have we built? We have built 256 models. So, we have model 0, model 1, model 2, all the way until model 256. So, what we've done is, we have taken the first byte of all the plain texts and we have built a power model, and we have tried to repeat this for all possible values of the key byte, starting from 0 until 256. Cool. So now, this is what we call as the power model matrix. So now is the final step of the attack, where you're going to compare or you're going to correlate the power model matrix with the real trace matrix. The real trace matrix is what is the data in the file that I've given you that contains the actual power traces. So the actual power traces also is a matrix, right? If you think about it. So can you tell me what is the size of the actual power matrix? So the actual power matrix is something that's present in the waveform file. Yeah. So can you tell me what is the size of the actual power matrix? So let's say the actual power matrix is for plain text 0, the encryption looks like this. For plain text 1, like this. Plain text 2, so on. So now if, and how many points are there in this trace? How many points are there? 2500, right? So if you just compute how many points are there from here to here, then that will be 2500. Then 2500 points. And so can you tell me what is the size of this matrix, actual power matrix? How many rows and how many columns? 100 rows. Why? Because you have 100 encryptions and you have 2500 columns. Am I correct? So you have 100 rows and you have 2500 columns. And can you tell me, or do you agree with me that the SBox operation is one among these 2500 columns? So you have 2500 columns for this matrix, right? Now, do you agree with me that the S-box operation is one among these 2500 columns? Yeah? But you do not know where the S-box operation is happening, right? You do not know where it is happening. It could happen here, it could happen here, 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 here. Anywhere among these 2500 points, the S-box operation could happen. So you do not know where exactly it happens. So what do? You simply brute force. So you try to match with all the possible columns. So this is the final step of the attack, wherein you take the, so you basically take every possible column of the power model matrix and correlate it with every possible column of the actual power matrix. Is this clear? So you take this vector, the first model, you correlate it to the first column. You correlate it to the second column, third column, and so on. And when you correlate, you actually get a correlation score. So you can call it, you can also refer to it as a matching score. So you take the first model and you match it with the first column. You take the first model, match it with the second column, and you simply match the first model with all the columns. Then you move to the second model and match it with all columns. You move to the third model and match it with all columns, and so on. So let's try to understand that a bit. Good. So your power model matrix basically has Do you agree with me? There are 256 models. The number of rows is 100 and the number of columns is 256, right? And now the actual power matrix has how many columns? It has column 0, column 1, column 2, column 2500. The columns basically indicate time. So there is the first time point, time sample, second time sample, third time sample, all the way to 2500 time samples. So it has 100 rows and 2500 columns. So what do? Is you take the first model and you match it with all the possible columns. So the matching is done using something called correlation. So let me explain what correlation is. Correlation is like a statistical metric that tells you how similar two vectors are. So for example, if your vector is, let me explain correlation. So let's say if one vector is like this and if the other vector is like this, then do you think both have a high correlation? They do, right? Why? Because they follow a similar trend. They look similar. It doesn't matter how close the values are, it's about the trend, whether they look similar. So for example, if the temperature of the city goes higher, then the number of ice creams that get sold or the number of orange juices that get sold goes higher. So that's the correlation. And if the temperature gets lower, then the sales of all these cold items also go down. So that's the correlation part of it. So if, for example, if you have a vector like this, do you think this and this correlate well? The correlation is slightly lower, right? Because it doesn't, the trends do not follow. And if it's something like this, then there is no trend at all. If this increases, that doesn't mean that this increases. So correlation is basically trying to find how similar two vectors are, and we're going to use this correlation metric to actually match this column with this column, all columns of the power model matrix with all columns of the actual power matrix. So, and you're going to compute what's called as a correlation So you're going to compute correlation score matrix, and by looking at this, can you tell me what is the size of the correlation score matrix? So how many rows will be there and how many columns will be there? So I have 100 cross 256 and 100 cross 2500. So can you tell me how many rows will be there in the correlation score matrix and how many columns? So let's try to do that. Let's try to manually calculate. So you take the first model and you correlate it with the first column. So let's say you're finding the correlation of the first model with the first column, and then you do the same first model with the second column, first model with the third column, and all the way until first model with column 2500. So how many rows are there? Sorry, how many columns are there? 2500, right? And now you simply repeat the same for the next model, which is the next key byte value or the next possible value of the key byte. So one thing to remember is this model corresponds to the key byte value of 0x00, 0x01, 0x02, and so on until 0xf. Right? So now you take the second model, which is 0x01, and correlate it with all the columns, and so on. And how many such models do you have? You have 256 models, right? So you have 0xff with column 0, 0xff with column 1, all the way until correlation of model 0xff with column 2500. So now can you tell me how many rows and how many columns are there? So there are 2500 columns and there are 256 rows. Am I correct? There are 256 rows and there are 2500 columns. And each row basically corresponds to every possible value of the key byte. Am I correct? So row 0 corresponds to key byte value 0. Row 1 corresponds to key byte value 1 because you're using, in row 0 you're using model 0. In row 1 you're using model 1, model 2. So every row corresponds to the key byte and every column corresponds to the time sample in the actual power trace, right? So if you compute this correlation score matrix, you will find one element that has the highest value. If you compare the correlation scores, you will find one element that actually has a very high value. So let's say this is that particular element that has the highest value, and let's say this particular element is present in row X and column Y. So let's assume this particular element is present in row X and column Y. Now can you tell me what's the value of the key byte then? So what's the value of the key byte that you have recovered? X is the value of the key byte, right? Because what you have identified is there is model X in row X that has correlated very well with column Y. So X is basically my key byte value from the attack and Y is basically the time sample at which the S-box operation is happening. Because you actually built a power model for the S-box of the first byte, right? So that will actually correlate with the time sample that manipulates that particular S-box value. So I know it all might get too confusing, but I hope like you at least got the sort of a general idea about this. So let me explain again, and let me try to explain just briefly. I won't bore you too much, but the idea is like you are building models for every possible value of the key byte. You don't know the key byte, you're trying to recover it. You don't know the key byte, so you're trying to guess for all possible values of the key byte. You're building models, and you're trying to now match this particular power model with all possible columns of the real power matrix, because you're trying to model the S-box operation. The S-box operation is present in one among these 2500 columns. So you're simply matching every possible model with every possible column, and whichever model corresponds to the correct key byte will match with that column that corresponds to the correct that corresponds to the time sample of the S-box operation. So if you do this computation, you will basically figure out one particular element having the highest value, and the corresponding row is nothing but the key byte, and the corresponding column is nothing but the time sample when the S-box operation is basically happening. So this is basically the attack. This is how it's done, and this attack is called correlation power analysis, because you're using the correlation matrix, or you're using the correlation statistical metric for your analysis. Any questions or doubts here? I'll give you like just 2 minutes on this one. Then we will just do one last Python exercise, programming exercise, and then we will conclude the lab. Okay. So let's go to the Python program. In the Python program, what I have done is I have actually taken one column of the power matrix, of the actual power matrix, like the real power trace, and I'm trying to find out which model actually correlates the best. So I have taken one column corresponding to the S-box operation, and I have tried to see which model matches the best with this particular column. So if we go to the Python program, here basically I have a code to generate the trace. Let me just copy the entire program. So now you can just go ahead and execute the CPA implementation.py script. Where is it? Okay. So I'm just executing the CPA implementation.py script, and what I've done is I have generated an artificial trace corresponding to the key byte 21, and now I'm basically correlating. You remember the correlation, the final correlation operation, right? This is where I'm actually taking the power model matrix. I'm taking every possible so I'm basically taking every possible model in the power model matrix and correlating it with this particular column here. So the column is nothing but the actual power trace. So I'm correlating every possible model in the power model matrix with the actual power trace using this particular function, the correlation function. So the correlation function is inbuilt in Python. It's available as this particular function here, and I'm simply computing the correlation values. And now what I'm doing is I'm also just plotting the correlation values here, and if you execute this program, you will see Yeah. If you execute this program, you will see that this is the correlation of all the models with one particular column. And here you will see that one particular key byte has the highest value, and this is nothing but the correct key byte. So you see, for 21 has the highest correlation value, and 21 is basically the correct key byte that was used. So in this particular simulation, I have generated the power trace for 21, and when I implement the attack, I'm able to recover the exact value of 21 from my attack. So you see this one, and you can actually play around with this script in the following manner. So you can ask the question, I have used 100 traces to do the attack, but what if I use just 50 traces? Will the attack still work, or will the attack fail? So let's try that. So you can just reduce 100 to 50 on top, and then simply execute the script again. And you will see that the attack still works. The attack still works. Now let's try to reduce it to maybe 5 traces. You see, when I just use 5 traces, I'm not able to obtain enough correlation, and the attack basically fails. So in order for the attack to work, you need a certain minimum number of traces. Obviously this is a simulated program, so just 20 or 30 traces would be sufficient for the attack. But when you're actually attacking a real device, there'll be a lot of noise in the measurements, and if there are a lot of noise, then the correlation will basically not be as good as what you're seeing here, and because of that you would need much more number of traces to actually attack it. So let's also play around with that. So in the program there's also a parameter called noise standard deviation. So let's say I'm increasing the noise standard deviation to a very large value, let's say 1, and even if I increase the number of traces to 100, you will see that the attack still fails. Why? Because the noise. So in the Python program, I'm simulating the noise to be very high, and if the noise is very high, even with 100 traces, the attack still doesn't work. So let's try to increase the number of traces to maybe 500, or let's just start with 200. With 200, you see that for 21 it's slightly increasing. You see there's a slight increase here. So if you just zoom in, for 21 it's still high, but you don't have enough confidence. You would still say that I do see 21 having the highest correlation, but I'm not very confident that it's actually the correct value. So what I would do, I would increase the number of traces even further. So what I would do is I'll simply say, instead of trying the attack with 200 traces, let me try with 300 traces. And if you try the attack with 300 traces, you would see that the correlation now drastically, so there is a clear winner here. You see, the other values are much lower, there's a clear winner. And now if you keep increasing the number of traces, then for example if I increase it to 1000, then there'll be a clear winner. So this is how CPA basically works, and the attack basically depends on how many traces you capture, and if there is a lot of noise in the power measurements, then you would need many more number of traces to basically break the implementation. Yeah? So this basically concludes the side channel attack lab. I hope it was interesting and fun. What we expect out of you are two things. One is a lab report, which is again an individual lab report. I'll give you the format of the side channel attack lab report on NTU Learn. And the second thing is the lab project, which is 20%, but it's a group project, so don't worry, you don't have to do everyone. You can just make one submission per group, and the topic for the lab project is you're supposed to implement the CPA program on the waveform file that I've given you. And you're supposed to recover the entire key, not just the first key byte, but all the 16 key bytes. Is that clear?
CPA strategy.
So I've already given you the CPA implementation on some simulated power trace. Now you're supposed to understand the concept and implement CPA on this particular waveform file and recover all the 16 bytes and submit the code and submit the result, the analysis and stuff like that. Is that clear? Cool. I think that's about it. You have to write just a very brief lab report, a project report on how did you do the analysis, what are the steps that you did, and blah blah blah. The report for the format for the project report will also be given to you. I think the deadline is about May 1st or May 2nd or something like that. I think you have sufficient time to work on it. And we'll also be sharing the recording of this particular lab session as well, so you can go through it later to understand the concept better.